Next, we'll take a look at a photoelectric effect example problem. In this example, an ultraviolet light beam having a wavelength of 130 nanometers is incident on a molybdenum surface with a work function of 4.2 electron volts. What is the stopping potential? So we know that for the photoelectric effect that the maximum kinetic energy of the electrons is equal to the energy you get from a photon minus the energy it takes for the electron to escape from the metal, so the work function. In this case, the work function is 4.2 electron volts, and we are given the wavelength of the light, which tells us about the energy. So another way of writing this same expression is that the maximum kinetic energy is equal to hc over lambda minus the work function. So here we've just made use of the wave equation for light, where the frequency times the wavelength is equal to the speed of light, and then rearrange that so that frequency is equal to c over lambda, and then substitute that in for the frequency. So we're given the wavelength, and we also know the work function, so we can calculate what is the maximum kinetic energy of the electrons that are liberated from the metal. Now, it turns out that this kind of problem is a little bit easier to do if we keep everything in terms of electron volts. So we know what the work function is in electron volts. Let's calculate the photon energy in electron volts as well. So this photon energy, which we sometimes write as the energy sub gamma, gamma representing the photon, is equal to hc over lambda, and we can put in numbers for that. So h is Planck's constant, which has a value of 6.63 times 10 to the minus 34 joules times seconds. The speed of light is 3 times 10 to the 8th meters per second. And then we're given the wavelength of the photons, which is 130 nanometers. So that's 130 times 10 to the minus 9 meters. So that's going to give us a photon energy of 1.53 times 10 to the minus 18 joules. And as I mentioned before, it's a little bit easier for this kind of problem to work in electron volts. So I'll convert the joules to electron volts. So we remember that 1 electron volt is equivalent to 1.6 times 10 to the minus 19 joules. So that means we're going to have 9.56 electron volts. So that's the energy of each photon. So then if we want to calculate the maximum kinetic energy that the electrons get, we take the energy of the photon, which is 9.56 electron volts, and subtract off from that the work function. And the work function for molybdenum is 4.2 electron volts. So then we get a maximum kinetic energy of 5.36 electron volts. So that is the maximum kinetic energy of the electrons. So if these electrons have a kinetic energy of 5.36 electron volts, and then we want to figure out how much voltage is required to stop them, then we know that there's that convenient relationship between electron volts and potential difference, which in this case is the stopping potential. So to bring these electrons to rest, it's going to take a potential difference equal to 5.36 volts. So if I have a kinetic energy in my electron of 5.36 electron volts, the stopping potential that I need is then 5.36 volts. And that would be the answer to this problem. 5.36 volts is required to stop the most energetic of the electrons. So next we want to consider X-ray production. Producing X-rays is kind of like the photoelectric effect run in reverse. So with the photoelectric effect, you had the energy of a photon becoming the kinetic energy of an electron. And with X-ray production, the kinetic energy of an electron becomes a photon. So the way that X-ray production works, so if you go to your dental office or you get an X-ray of your hand or your arm, what's going on in that X-ray machine is that you have a filament which is heated to a high temperature so that electrons can leave its surface. Then you have a potential difference, and that potential difference is very high, and so the electrons zoom from the negatively charged surface where they leave that filament to a positively charged surface, and there's a very big potential difference, and so they're moving very fast by the time they reach the positively charged surface. Once there, they slam into the atoms of the positively charged surface, and their kinetic energy gets turned into a photon. So that means we can calculate what the wavelength of this photon must be. So if we take the energy, the kinetic energy that the electrons get by being accelerated through the potential difference, then that becomes equivalent to the energy of the photon that's produced, which is Planck's constant times the frequency, the maximum frequency of the photon that can be produced. And then that would be equal to hc over lambda. So if we rearrange this equation for the minimum wavelength that can be produced by this process, we'll find that it's equal to hc divided by the kinetic energy that the electron can achieve. So this is the minimum wavelength because it is possible that not all of the kinetic energy of the electron becomes the energy of the photon. Some could be lost in this process, but if all of it is perfectly turned into a photon, then this is the minimum wavelength that the photon can have. So here's another question for you. Let's suppose you're designing an X-ray machine and you want to increase the wavelength of the X-rays. What should you do? Should you increase the voltage to the machine, decrease it, or will changing the voltage not matter?